Welcome to another session of differential geometry class. Today we are going to deal about vector fields on surfaces. Vector fields we have already seen. Now we are going to study about vector fields on surfaces. So before going to that, we will want to have some definitions. So the first definition we want to study is vector fields on an n surface. So definition. Suppose we have got a surface here and a vector field on each point of this surface, right? A vector field x on an n surface S subset of Rn plus 1 is a function which assigns to each point P in S a vector x of P belongs to Rp n plus 1 at P. And now this is called a vector field on surfaces. Okay, so each point we want to have a vector. So like this. Then we will say that it's a vector field on a surface. Now some two particular cases we are dealing. Suppose this vector field is lying in the tangent plane. We know that SP will denote the tangent plane and SP perp will denote the normal plane. So it says that whenever this XP, we are writing this as in this fashion, x of P is lying in your tangent space SP, then we will say that this is going to be a tangent vector field. Okay, for each P belongs to S, X is said to be tangent vector field on S whenever if X of P is a tangent to S. Whenever your X of P is a tangent to S, we will say that X is said to be a tangent vector field on S. Now similarly, if X of P is orthogonal to S, that is lying in the normal plane, for each P belongs to S, then we will say that X is normal vector field on S. So here what we are going to do is, one is vector field on surfaces, second one, whenever this vector field belongs to the tangent plane, we will say that it is a tangent vector plane, and whenever it belongs to a normal vector field, a normal plane, then we will say that this vector field is a normal vector field. So here's two example. We have taken one sphere. So in one sphere, you know that the tangent is always perpendicular to the radial vector, right? So when you are having here the radius, so this should be perpendicular to that. So here also, when you are having the radius, this should be perpendicular. So like that we are considering. Now this is going to be a tangent vector field, and this is going to be a normal vector field. See, whenever considering these two means perpendicular to this, right? So like this one picture will come. So this is example of tangent vector fields and normal vector field on a one sphere. Now another definition is smooth vector fields. So definition 2. A function, see here the problem is that whenever you are dealing with smoothness, we are always going to deal about open sets, right? We are define the smoothness in open sets, but here in surfaces we will say that a function in an n surface is smooth. So what's the meaning of that? That is this definition. A function g from S to Rk, where S is an n surface in Rn plus 1, is smooth, surface is smooth, if it is the restriction to S of a smooth function g tilde from V to Rk defined on some open set V in Rn plus 1 containing S. So what's the meaning of this? So suppose we are having a surface G from S to RK, where S is an n surface. So we have got an n surface here. This is your S. Now from S to I'm mentioning my RK, something like this. This is my RK. Now for the visualizing basis only I am drawing this. It's not the actual drawing. We cannot draw RK and all, right? So from here to here we are defining your G, and we are saying that this G is smooth. So G is smooth means the meaning is that there exists an open set V, and from this V to RK we have got a function called G tilde, such that G tilde is restricted to S is nothing but your G. Can you follow? So whenever you are dealing with surfaces and we are saying that a function is smooth, its meaning is that the function is smooth, or the function can have an extension from an open set to RK, and this extension is going to be a smooth field. So similarly, a vector field X on S is smooth if it is the restriction to S of a smooth vector field defined on some open set containing S. So here we have dealt about a function. So in particular, whenever we are dealing with vector fields and we are saying that the vector field is smooth, the meaning is that there exists an open set and this vector field can have an extension to that open set, and that is smooth. Thus X is smooth if and only if X from S to R plus Y is smooth, where this we will say that associated function, right? So we are having here this X of P is equal to P comma X of P, and we will say that this is smooth whenever this one is smooth. That is, we will call this as associated function, right? Associated function. So this is the meaning of smooth vector fields. So we have studied about vector fields on surfaces and smooth vector fields on surfaces. Next we are having a theorem here. It says that the existence and uniqueness of a maximal integral curve. See, this is the maximal integral curve. So this theorem can also be asked as state and prove. State and prove the existence and uniqueness of a maximal integral curve in an n surface. So the same theorem can be asked like this also, right? So when it's asking in such a question means we have to first state this theorem, then we have to prove it. So let us see what this theorem says. Let S be an n surface in Rn plus 1. Let X be a smooth tangent vector field on S, and let P belongs to S. Then there exists an open interval I containing 0 and a parameterized curve alpha from I to S such that alpha of 0 equal to P, alpha dot of T equal to, that means this is nothing but tangent vector, and we will say that velocity vector, right? And evidently this will belongs to your tangent plane. So your x of alpha of t is a tangent vector field for all t belongs to I. Second one, if beta from I tilde to S is any other parameterized curve in S satisfying condition 1 and 2, then this I tilde is contained in I, or we can say that beta of t equal to alpha of t for all t belongs to I tilde. That means your this is your I and this is your I tilde. That means when you are having a beta, means it should be some restriction of alpha, nothing else. Now the second statement says that a parameterized curve alpha from I to S satisfying condition 2 is called an integral curve. We have already seen this one. Satisfying this means we will say that this is an integral curve. And next thing is that of the tangent vector field X, as I already said, x of alpha of t is equal to alpha dot t denote that this x of alpha of t is a tangent vector field. The unique alpha satisfying conditions 1 to 3. So whenever you are having an alpha satisfying these 3 conditions, that such an alpha is unique, and that is called a maximal integral curve of x through p. So that's why we are saying that the existence of a unique maximal integral curve on S. So we want to prove this. How to prove it? You can see. So first of all, we will use the idea that X is a smooth vector field. Proof. Since X is a smooth vector field, X is a smooth vector field, there exists an open set, say V, such that, or containing S, or such that S is contained in V, and a smooth vector field, let me take it as x tilde on V, such that there should be another condition, such that this x tilde of some q is equal to x of q for every q belongs to S. That means it should have an extension, nothing else. Q belongs to S. Now let F from U to R and C belongs to R. They give me that S is a surface, so we want to represent S as some level set. That's why we are defining such a function. Be such that S equal to this F inverse of C, and del F of some Q not equal to 0 for every Q belongs to S. This means that S is a surface. For all Q belongs to S. Now let W equal to set of all this Q in Q belongs to U intersection V, such that del F of Q not equal to 0. So that means you are taking the points from the surface and your V, right? So Q belongs to U intersection V such that del f of q is not equal to 0. Then W is an open set. Then this W is an open set containing S. Containing S. And both x tilde and f are defined on W. Are defined on this W. Now let Y be a vector field. Let some Y be a vector field on W, comma, everywhere tangent to the level set of tangent to the level set of f. Set of f are defined by or defined as, we are defining y as y of q is equal to x tilde of q minus x tilde of q dot del f of q by norm of del f of q square into del f of q. This you have seen previously also. This meaning is that we are deleting the del f of q component from your x tilde of p. Now for all q belongs to S, we are having y of q is equal to x of q. Is it true? We are having y of q is equal to x of q. Just a substitute for q belongs to S, we will get this equal to x of q. What's the reason? Y of q for all q belongs to S means q belongs to S, right? So this belongs to x tilde of q belongs to which one? It belongs to the tangent space, right? Belongs to tangent space. And del f of q belongs to normal space. So what you're having is x tilde of q dot del f of q should be equal to 0. Since x tilde is tangent, we are having del f of q should be normal. So this equal to 0. So this equal to 0 means this entire quantity is equal to 0. Now this entire quantity equal to 0 means your y of q should be nothing but x tilde of q. Or we can say that x tilde of q is nothing but x of q whenever q belongs to S. So we are having y of q is equal to x of q for all q belongs to S. Now let alpha let alpha from I to W be the maximal integral curve, be the maximal integral curve such existence of a maximal integral curve we have already seen in your integral curve chapter. So maximal integral curve of y through p then alpha actually maps I into S, because what is I? I means domain of your alpha and S means our surface, right? So definitely this alpha will maps I to S, because F composition alpha dash of t using chain rule is nothing but del f of alpha of t dot alpha dot of t. Now this is equal to del f of alpha of t. What is alpha dot of t? Alpha dot of t is y of alpha of t, and this is equal to 0. Reason is, since f of alpha is a constant, since f of alpha of t is equal to c, some constant, so its derivative should be 0. So this entire quantity will become 0, and your f composition alpha of t or alpha of 0 is equal to f of p. Now f of p is c. So what you conclude is, so f composition alpha of t is equal to c for all t belongs to I. Now for condition 1, what was first condition? Alpha of 0 is equal to p. So for condition 1, we have already observed that alpha of 0 is equal to p. Now alpha dot of t is equal to y of alpha of t for every t belongs to I, which implies x of alpha of t is, we have seen that this is x of alpha of t for t belongs to I. Say the bracket, we can write, since q belongs to S, in S x of alpha or x of q is nothing but y of q. Both are same, we have already seen this. Now for this condition 2 is satisfied. Thus condition 2 is satisfied. Now we want to prove the condition 3. So condition 3 is also satisfied, because any parameterized curve. What was the third condition? If there exists a beta which having the same property, then this beta should be a restriction of alpha to some subintervals of I. So because why they are saying like this? Because any parameterized curve beta from I tilde to S satisfying condition 1 and 2 is also an integral curve of the vector field Y on this W. So by the uniqueness of integral curves, of vector fields or vector field Y on the open set W, we get a beta of t is nothing but some alpha of t for every t belongs to I tilde. So this is the proof of our theorem. So in proof, first what we have seen is, first we are using the idea that our vector field is a smooth one. So since that is going to be a smooth one, we can find an open set V. And next case is what we are going to do is, we will pick it out the function which is used for defining our surface S, that is F. Now with the domains of these two, we are going to define a set W. This set W as a set of all Q belongs to U intersection V, such that del F of Q not equal to 0. And the first thing we want to observe here is that then here we can define one more vector field Y of Q, namely as x of q minus x tilde of q dot del f of q by norm of del f of q square into del f of q. Now this y of q and x of q are the same on your surface S. That's the first thing we want to note. And next we can have a maximal integral curve alpha of y through P. Now what you're going to do is, we will prove that f composition alpha or f of P equal to some C, and we will show that the condition, first condition, that is alpha of 0 is equal to P. Next thing, we will prove the second condition, and lastly, using the maximal integral curve idea, we will get the third condition. Now it has got a corollary also. Corollary is like this: let S equal to f inverse of C be an n surface in Rn plus 1, where f from U to R is such that del f of Q not equal to 0 for all Q belongs to S, and let X be a smooth vector field on U whose restriction to S is tangent vector field on S. Now if alpha from I to U is any integral curve of X such that alpha of T naught belongs to S for some T naught belongs to I, then this alpha of T belongs to S for all T belongs to I. So we want to prove this. I repeat, first we are having a surface S and f from U to R is such that del f of Q not equal to 0 for all Q belongs to S. So up to that means we are having a surface, and let X be a smooth vector field on U whose restriction to S is a tangent vector field on S. Now if alpha from I to U is an any integral curve of X such that alpha of T naught belongs to S for some T naught belongs to I, then what you are having is this alpha of T should be inside the surface. So let us see how we can prove it. Proof. Suppose alpha of T, proof by contradiction method, suppose alpha of T does not belongs to S for some T belongs to I, comma, this T is greater than T naught we are saying. Let T1 denote, let T1 denote the greatest lower bound, GLB we will say, of the set, we're defining the set as set of all T belongs to I such that this T is greater than T naught and alpha of T does not belongs to S. Okay, T belongs to I and this T is greater than T naught and this alpha of T does not belongs to S. Then f of alpha of T is equal to C for T naught less than or equal to T less than or equal to T1, because if T1 means it does not belongs to your S. See, so when you are taking T values which is less than T1 means definitely that it will belongs to your surface. So by continuity, f of alpha of T1 is also should be equal to C1. Equal to some C. So how we got this? It's nothing but C, right? So how we are getting is we having f of alpha of T1 equal to limit T tends to T1 of f of alpha of T, right? So this equal to limit T tends to T1. What is f of alpha of T? C, right? So we'll get this entire quantity as C itself. So we are having f of alpha of T1 equal to C. That is alpha of T1 belongs to S, our surface. Now let beta from I tilde to S be an integral curve through alpha of T1 of the restriction of the restriction of x to s, x to s, then beta is also an integral curve, also an integral curve of x, integral curve of x, sending 0 to alpha of t1, as in the case, as in the curve alpha tilde defined by alpha tilde of t is equal to alpha of t plus t1. Then definitely when you're having 0 means alpha tilde of 0 is alpha of 0 plus t1, that is alpha of t1. Then by uniqueness of integral curves, then by uniqueness of integral curves, integral curve, alpha of t should be equal to alpha tilde of t minus t1, alpha tilde of t minus t1, and that's equal to your beta. So this is equal to beta of t minus t1. I have written as beta tilde. No, okay, that's a mistake. This is equal to okay, this is equal to beta of t minus t1, because every t minus t1 belongs to s, right? Belongs to s for all t such that t minus t1 is in the common domain of alpha tilde and beta. But this contradicts the fact that alpha of t does not belong to S. But this contradicts the fact that we have assumed that it does not belong to S, right? So contradict the fact that alpha of t does not belong to S for values of t arbitrarily close to t1. Hence, what we can conclude is, hence alpha of t belongs to S for all t belongs to I, with the condition t is greater than t naught. Now similarly we can prove that t less than t naught case also. So this implies the corollary. So hence the corollary. So this is the corollary. Once again, we are noting the corollary here. That means S is an n surface in Rn plus 1, where F is used to define your surface S, and X a smooth vector field on U whose restriction to S is a tangent vector field on S, and if alpha is an integral curve of X such that alpha of t naught belongs to S for some t naught belongs to I, then your alpha belongs to the surface. And today we have seen a theorem, the uniqueness and existence of a maximal integral curve and one of its corollary. So hope you understood today's class. I'm winding up the session here. Thank you for your patient listening. Thank you.